Hello, 20-1s. Great day for some practical applications of quadratic functions, also known as everyone's favorite, word problems. All right, because we've been dealing with quadratic functions, which are parabolas, you actually do have practical applications when you have a parabola, and a lot of questions resemble the same kind of situation in terms of what you will understand, because there's a lot of objects that travel in a parabolic arch. Any projectile, you could say, that's tossed up will take a parabolic arch. If you throw a ball, the ball goes up, reaches its max, and then comes down. Is it a perfect parabola? Probably not, but we can assume that it's taking a very parabolic quadratic function type of direction. So those are the popular questions. We're then going to look at two unique situations, area problems and income problems. These are two unique situations where quadratic functions do have a practical application. Again, like I've said so often, not necessarily in everyday, everyone's kind of life, but they are practical applications nonetheless. So here we go. Let's take a look at page 14, practical applications. We're looking at example number 2. So the path of a basketball shot is modeled by that quadratic function. So we have to have an understanding, first of all, of what the parabola represents. If I have a quadratic function and we graph it, and we're going to, in this case, because the values are kind of ugly, this could be done on the calculator, using the calculator to get your values. But first of all, our t values, which are time, that represents the x-axis, because that's our independent. It's the time that changes first. So we're looking at time on the x-axis, and h at t is saying what's the height at a certain time. So height is our y-axis. So if you were to punch this into your calculator, you would get a parabola that looks kind of like this. It's not perfect, but the parabola looks something like that. Now, in terms of the path of a basketball shot, all of the parts that we've talked about, the characteristics of a parabola, really are important pieces for answering the questions. Because remember, our x-axis is time. Well, our vertical axis represents a time of 0 seconds. So if we take a look at this, really this part of the graph doesn't exist because we can't have negative time in terms of a basketball shot. However, what is important to understand is that our basketball shot at 0 seconds actually doesn't start at a height of 0. The height starts up. Why would that be? Well, because, and here comes a really great, if I have a basketball player and they're taking a shot, they're not shooting from the ground, so the basketball flight actually starts at a bit of a height. So we're not starting at the origin, we're starting at a y-axis, a y-intercept value. Besides that, we have the vertex, which we've talked a lot about. Well, what does the vertex represent? Well, this is the maximum height that the ball reaches. The ball leaves the hands, it goes up to a maximum height. But not only is the maximum height our y value, well, at the maximum height, our x value, that's how long it takes for the ball to travel to the maximum height. So this parabola, yes, it's a parabola, but all of these characteristics give us, honestly, important information if we're analyzing the path of a basketball. The last one in this case, well, we have our x-intercept down here. Well, what does that represent? Well, if it's on the if our x-intercept, which means our height, how high are we in terms of the y-axis? We're at 0. Well, that's where the ball hits the floor. If it hit the floor, if someone didn't catch another player, the ball would go up, reach its maximum height, come down and hit the floor. All of these parts of the graph are key parts for this question. So let's take a look at this using our calculator. So again, without as much scribbling, here's the information that's given. The first question is, what's the maximum height? Well, the maximum height is our Q value, or the Y in our vertex. Remember, vertex is always PQ, so the Q value will be the maximum height. So let's, if you haven't already, plug it into our calculator and see what we get. All right, just needed to make it a little smaller to fit the window there. So what do? Y equals, and y is equal to, please remember it's a negative 1.2x squared, don't use a subtraction sign, plus 3.3x, or the t, plus 2.2. And now we graph it. Now, the graph, it shows all the important parts. I'm going to change my window settings a bit just so I can see everything specifically. My y, or my x min value, can be brought in. I don't need it way over here. I don't need all of this y min value. And I could even bring my x max in a bit. So I can change those so I see the graph really nice. So I'm going to go to Window, change my settings. My x min can be smaller, -2. My x max doesn't have to be quite as big, 7. My y min, we talked about bringing up, -2, and I'll leave the y max if I graph that. Well, I could technically have brought it down a bit, but I've got all the information I need. So like we said, we want to figure out what's the maximum height of the ball. That's what we're looking for. So we need to simply second trace. This is a maximum value because our parabola opens down. And now I simply scroll to the left of our vertex, hit enter. Scroll to the right side of the vertex, hit enter. Yes, please guess it. And because it's a word problem, because we talk lengths in terms of decimals, it's okay to leave these as decimals. So we have a 1.4, 4.5 for a vertex. Our vertex is at 1.4 and 4.5. So what's the maximum height? The maximum height reached is 4.5 meters, depending upon what it tells you to round it to. Second question, what's the time to reach the maximum height? Well, remember, time is our x-axis, so the maximum height occurs here at, there you go, 1.4 seconds. So our vertex tells us a couple of key pieces of information. Next, we were to ask, what's the y-intercept and its meaning? Well, we already talked about the fact that the y-intercept is where the basketball player would have released the ball from. They don't release it from the floor. They're standing a certain height, their arms get extended. So this, at 0 seconds, is where the ball is released from. So the y-intercept is the release point, or the initial spot the ball leaves from. And how do we find that? Well, we can go back to our graph. This time, we want second trace. And to get the y-intercept, we want the value when x equals 0. Because our y-intercept always occurs when x equals 0. And we can see the y-intercept is 0, 2.2, which tells us 2.2 meters is our y-intercept. The release point is 2.2 meters high. And there you go. Last one, when the ball hits the floor, Well, the ball is released, it travels to its max, it comes down, it'll hit the floor and then start bouncing. But here's where the ball hits the floor, which is our x-intercept for the right intercept point. So we can go back, we want second trace, we want the 0 value. Scroll way over, and again, this one's a little tricky. We want initially to be on the left side of the intercept. So if there's the intercept, we initially want to be left of the intercept, which means we need to be above it. For this case, we need to be slightly above the intercept, hit enter. Now it wants to be to the right side of the intercept, and to be on the right side of the intercept, we need to be below it. Hit enter, guess it, yes, please do. Remember in another video, 1e to the negative 12. That just means I moved the decimal 12 places to the left because it's negative. That's like saying 0. So our x value is 3.3 when y is 0. So from there, go back to our question, and we have 3.3, which represents 3.3 seconds from the time of release to when the ball hits the floor. So a parabola and all of the characteristics of it are key pieces of information. So let's take a look at page 15, example number 3. Same kind of question. It wants to know the height above the green of a golf ball hit from an elevated tee. So those of you that don't golf a lot, here's the tee. That's essentially what you're hitting the golf ball off of. So you tee off, it travels, and then hopefully it hits the green where the hole will be and the cup. So that's what the question's saying. We're hitting a golf ball off of an elevated tee. It travels in a parabolic quadratic function path to hopefully hit the green at some point. There's what this question's asking. Now the big difference with this question is the fact that our quad function, whole numbers, it's manageable in this case to actually create. And instead of solving with the calculator, you should be able to turn it into vertex form and then use that information for some of these questions. Pause the video, turn it into vertex form, see if you can answer the questions, and then we'll do it. Same question, but this time, try to do it manually instead of with your calculator. But question C, manually, you can't do. A and B, we can do it manually. C, we'll have to use the calculator, but try it algebraically first. Pause the video, away you go. All right, so vertex form. First step, we want to factor out the negative 2 so that we have just a t squared. If we divide everything by negative 2, it'll be a t squared minus 10t, and we still have the plus 42. What's the next step? Well, the magic step, that quirky little step that you do, take the t coefficient, divide it by 2, and then square it. So we're left with negative 2 bracket t squared minus 10t. Negative 2 divided by 2 is negative 5. Negative 5 squared is a positive 25. And we still have plus 42. However, remember, we've added a negative 25. We've changed it. But we didn't actually add negative 25 because it's in brackets. We've added a value of negative 50. I've changed it by negative 50. So let's add a positive 50. So mathematically, by putting both of those in, I've changed it by a value of 0. I've put in the stuff that I need, but really changed it by nothing mathematically. I can now factor, because I have a perfect square. This becomes t minus 5 times t minus 5, which is just t minus 5 squared. 42 and 50 is plus 92. So there's what we now have for our vertex form. What can we get from vertex form? Well, the first thing we can get is our 5 and 92, our vertex, our P and Q value. Well, again, in terms of this particular question, it talks about if you were to graph this, which we will in a second, you'll see the parabola looks like this because it tells us you're somewhere where it's an elevated T. So the T box where you're hitting from is above where the green is. So that's our y-intercept, but it's elevated and it goes up to the vertex, which we now know is 5 and 92. Now this is the same variables as before. 5 represents 5 seconds to reach the maximum height, which is 92. So the maximum height is 92 meters, which is hit, or it reaches at that point 5 seconds after the ball was contacted. There's your first question. Second question says, what's the height of the tee? So we want to know how high is the tee that we hit from. Well, that's our y-intercept. This is a y-intercept question. Hate to do this, but I'm going to erase the work that I have right now so I can do that because I've run out of space. But our y-intercept, remember, a y-intercept occurs when x equals 0. It's going to hit the y-axis when we haven't moved left or right. So I can say the height after a certain time of 0 seconds is going to be -2 times 0 squared plus 20 times 0 plus 42. Because our x is really just the time component. 0 squared is 0 times -2. 0 times 2 is 0. It's gone. 20 times 0 is 0. So what's the height at 0 seconds? It's 42. So the height of the tee is 42 meters up. So the tee is 42 meters up. The ball traveled 50 meters higher to a maximum height of 92, and then it would have fallen these 92 meters to land on the green. Now, time when the ball hits the green, well, it's going to hit the green at a t value or our x-intercept. Like I've said in some of the previous videos, x-intercept algebraically, it's not as simple as these other characteristics. It's as complicated enough that we do an entire chapter. Chapter 4 is all about solving for x-intercepts. So that would be done with your calculator. So you can check it with your calculator if you want, but if you check it with your calculator, you are going to have a time of 11.8 seconds. You can double check that on your own with your calculator. It's going to travel for 11.8 seconds before it hits the green. So this is the first type of questions, things that travel in parabolas. Those parabolas, the characteristics, give us important information. All right, we continue on. Page 16. Now we get into questions that the quadratic function is useful, and it's just a bit of memorization as to why. So what you're looking at with area problems are questions like, well, what they all are, but you're given a certain amount of fencing to create pens. So what we want to do is, for whatever kind of pen, we want to create a rectangle pen, but one extra bit of fencing to create 2 smaller pens, but we want a maximum area. Now, if I could play and guess and check all I wanted. Technically, I could have a 1 meter by 1 meter by 1 meter, which would be 237 meters left. And so then I could figure out how long the y's are. If I used had a pen that was 1 meter wide, so I would need 3 meters of fencing here, and then the 237 that gets left, I would divide amongst these two lengths. So divide that by 2, we would have 115, 115, 118.5, I believe. So I could have a pen that's 1 meter by 118.5 meters, because that would use 240 meters of fencing. That's one possibility. Well, another possibility, well, maybe we go 10 meters wide on each of these. So I would be using 30 meters of fencing. Well, 240 minus 30 leaves me with 210. Because 30 meters would be used here, well, that means I would have 105 meters for each of those lengths. So I could have a 10 by 105 meter total dimensions, and then I could get an area. So there's all kinds of possibilities for X and Y, tons of them. The key is we want to find which X and Y value gives us a maximum area. It's a step-by-step process. Here we go. The first thing is we want to create an equation to represent the fencing. Well, we know we have 240 meters of fencing, and that fencing is made up of 2 lengths that are Y long, so 2 Y lengths, along with these 3 X lengths of fencing. So there's our first step. 240 meters of fencing is based on 2 Y lengths along with 3 X lengths for this case. There's step 1. Step 2, we want to isolate the Y. We've done a lot of that over the years, so get Y by itself. I'll move the 3X over. So we have negative 3X plus 240 still equals 2Y. Now I divide by Y on both sides. Sorry, divide by 2 on both sides to get Y by itself. We're left with Y equal to negative 3 halves X plus 120. I've isolated Y. There's step 2. All right, now we need to get our equation. Well, we're looking at the area of that particular rectangle. Well, that's length times width, which in this case is identified as X times Y. So we have the area of that rectangle is X times Y. But I don't want 2 variables on that side. So what I can do is I can take my Y now, because I have an expression for Y, and say the area is the X length times the Y length. We now have an expression for the Y length, which would be negative 3 halves X plus 120. So a whole bunch of little steps to start to create the equation. An expression or equation to represent the fencing that was used. Isolate the Y. Now we know area is X length times Y length. So I put it into an equation, and let's distribute the X. A equals negative 3 halves X squared plus 120X. And what do we have when we have distributed the X? We now have the general form of an equation. So we end up with a parabola. Essentially, our area now from our quadratic function equation is our Y. Y equals negative 3 halves X squared plus 120X. It's a quadratic function. It's going to give us some form of a quadratic where the X value, whatever our X value is, will end up giving us a Y value, which is our area, which is a max. So that's why this works. We end up with the quad function independent variable x will result in our dependent variable y, which in this case really is representing the area. And we want where area, or y, is a maximum. So it all comes together. Goofy, but brilliant at the same time. So we now want to convert to vertex form. We've done a lot of that now. Careful, because we're dealing with a fraction. So our y will equal, after I group those, I have to divide by a -3/2. Fraction work can be done on the calculator. Be careful. Factor out a -3/2. We get left with x squared minus, after we divide 120 by -3/2, we get -80x. Well, what's next? Magic step. -80 divided by 2 squared. -80 divided by 2 squared. Well, -80 divided by 2 is -40. Squared is is positive 1,600. So we get y -3/2 x squared minus 80x plus 1,600. But remember, we've added that 1,600, but because it's in the brackets, we multiply by what's out front. We've added a -2,400, so we add the 2,400 on to balance it out, and let's finish it off. -3/2 bracket, perfect square becomes x minus 40 squared plus 2,400. And that is our vertex form. And once we have the vertex form, why that's useful? Well, our p-value 40 is the x dimension of the pen. And the q, like I just quickly showed on that diagram, is the maximum area of the pen. So the maximum area of the pen is 2,400 meters when x is a dimension of 40. But make sure you finish it off. We've now solved for the maximum area, which is 2,400. We've solved x to be 40. Make sure that you solve for the y dimension. Area is 2,400. Divide by the one dimension. That leaves us with 60. So y is 60. If you're going to build this kind of a pen with 2 sections in it using 240 meters of fencing, it will end up being 60 meters by 40 meters and have a maximum area of 2,400 meters. It just comes together brilliantly in a really interesting way. That's an area problem. A little bit of memorization of how to do it, but hopefully there's some understanding of why we're doing what we're doing. Let's take a look at number 2. Same kind of question, little bit different looking pen. It's going to be the same process. If you want, pause the video, give it a try. We'll do it together. But what's important with this one is to understand that this is an existing fence. So the 240 meters in this case, actually I shouldn't underline that with blue, the 240 meters of fencing, this is what's taking the fencing. They're putting it up against something that's already there, so we don't have to worry about that in our 240 meters. That'll be important in that first step of creating the equation to represent fencing. Pause the video, give it a try, and then we'll do it together. All right, here we go. 240 meters of fencing in this case. How is it being utilized? Well, there's only one length of y, but there are 1, 2, 3, 4, 5 x lengths. So there's our starting equation to represent fencing. 240 meters is used for 1 y length, but 5 x lengths. Isolate y. In this case, it's pretty easy. Just going to move the negative 5 over. Negative 5x plus 240. There we go. Now we know the area of this pen can be found by going x times y, length times width. But I don't want two variables there. I want to take my y and say the area is going to be the x length times the y length, but we're going to use that y expression instead of just a y. Distribute the x. Negative 5x squared plus 240x, where a is our dependent variable, or the y if we look at it from a vertex equation form. Took the equation, distributed it. We now have our general form. Let's go vertex form. Bracket our x's, factor out the negative 5, x squared minus, because 240 divided by the negative 5 leaves us with 48x. There's that step. What do we do now? Magic step over here, 48 divided by 2, and then square it. 48 divided by 2 is 24. 24 squared is 576. So area is negative 5, x squared minus 48x plus 576. Well, we added in that 576. But because it's actually negative 5 times 576, we added a negative 2,880. So we need to add that 2,880 on. So we've added a value of 0. Area is negative 5. Let's do the perfect square calculation, which will be x minus 24 squared plus 2,880. Here we go for this area question. What do we now have? Well, our p-value gives us our x dimension, which is 24 meters. Our q value is actually the maximum area. Maximum area is 2,880. So in this case, we now have a fence length of 24, 24, 24, 24, 24, and a y length, well, we need that y length, 2,880 divided by the 24 gives us 120. So we get 120 meters. So our pen is 120 meters by 24 meters to give us a maximum area of 2,880 meters. And if I double check, 240, 240, 240, or sorry, 24, 24, 24, 24, 24. Well, that, along with the 120, totals 240 meters of fencing. It all falls into place. Interesting. All the thinking goes into the setup, though, understanding what you have to do. All right, page 17. Page 17, we're now looking at income problems. Well, income problems. We are not talking about my problems because I spend more than I make. Income problems in this is very much an interesting and practical business idea, in the sense that businesses have to find the perfect combination of price of an object which will yield the highest possible sales. So, I mean, if a store were saying, hey, let's sell something for $1, $1, you know what? We're going to do 200 sales. Well, $1 at 200 sales is going to yield a certain income, $200 in income coming in. But maybe we don't have to sell, that's number of things, not price. Maybe we don't have to sell 200 things. What if we actually took the price and we moved it up to $2 per item? Well, the problem with changing a price and making a price go up, well, the number of sales is going to go down. Some people will say, well, I don't want to pay $2 for that. So maybe the sales goes down. And so instead of 200 sales for a dollar item, they're only going to make 150 sales at a $2 item. Well, wait a sec, that's still $300 profit income. We're making more than there. So companies need to try to figure out the perfect combination of how much to sell things at to give the best number of sales for that situation. I mean, a company could say, oh, I could sell 100 books, but if I just sold one book for $1 million, I'll be rich. But what's the chance of selling a book for $1 million? It's pretty slim. So they have to find the perfect scenario. So read this example, and then we'll take a look at how it works before we get into the quadratic function part of it. Because what we're looking at here is this says they're going to sell 60 books for $8. The income would be $480. Well, X in these questions represents the number of price increases. So 60 books at $8 means there hasn't been a price increase. Well, if they make one price increase, that means the number of books will drop by 6. So they're only going to sell 54 books, but they're now charging $10 per book. $2 increase, drop of 6 books. So if they make one price increase, they're going to have an income of $540. Well, that's a good thing. Absolutely. If they do a second price increase, their sales will drop by 6 more, down to 48 books. Well, but the price of the books will be $12. Well, if they can sell 48 books at $12, they're going to make $576. Fantastic. Still looking good. 3 increases. Drop 42. Price of book is 14. Well, now if they have 42 book sales at $14, that works out to be an income of $588. Still looking good. They're going to get greedy. Let's do 4 increases. Drop it by 6 more books. We're only going to sell 36 books, but we're now charging $18 per book. Well, 36 books at $18 per book. What happens? We are now doing $648 in income. So let's do a 5th one. We're now only selling 30 books at $20. Well, 30 books at $20, oh, now it's a problem. Because now, yes, they're making more, they're getting more for each book, but their number of sales has dropped where they're not bringing in the same amount of income as previously. What if they did one more increase? Well, that would be 24 books sold at $22. 24 books at $22. Oh, I messed up a little bit. Oh, I hate doing that. Mr. McDonald, you big doofus. If there's 4 increases, it would be 36 books at $16. My bad. So sorry. 36 at 16 is 576. Oh, I apologize. But we can see that here is where they start to drop. They had made $588 with 42 sales at 14, but that next price increase dropped the number of sales that they're not making as much money. If they did another increase, $30 a book at $18, well, $30 a book at $18, that means they're down to $540 income. So again, we start to see prices go down because, yeah, they're selling more per book, but the sales are getting too small. So that's what income problems are talking about. What's the perfect combination of price to number of sales? So, again, with these, very step-by-step procedural, but you just got to remember the setup. So here we go. It's going to look similar, but still be a little different. First thing, we want to create equations for price and sales. So, price. What do we know about the price of books? Well, we know the price of books is going to be $8. However, they're going to increase by $2. How many times? That's what we're not sure. X always represents the number of price increases. If they increased once, well, it would be 8 plus 2 times 1, which would be $10. If they increased 7 times, 2 times 7 would be 8 plus 14, which would be 22 if that was 7 increases. So we're not sure how many increases we're going to have. That's why we use the X. Now, the number of sales, what do we know about the number of sales? We know they make 60 sales. However, what happens is they're going to lose 6 sales for every increase X. So there's the key for this in your setup. Price, you need an expression. Sales, you need an expression. Income, how much they bring in is the price of the item times however many sales they get. So we, in this case, know that our price is 8 plus 2x times the sales, which is 60 minus 6x. There's our equation. Price times sales is how much you bring in. You now need to FOIL into your equation to get the general form. So when you do the FOIL process here, because it's a binomial times a binomial, I like to just make sure I write it in the correct order for general form. We end up with negative 12x squared plus 72x plus 480. Now we have our general form. We can convert to vertex because that's the important information. Income, here we go. Take out, divide a negative 12. Leaves us with x squared minus 6x. I'm going to cheat a little bit, leave some space, and add 480. Well, magic number, negative 6 divided by 2 squared is a 9, so plus 9. We've actually added negative 72, or negative 108, so we have to add 108 on at the end. Our income will be negative 12. Do the perfect square factoring. We get x minus 3 squared plus 588. So again, here's a vertex form of a quadratic. If I were to do a sketch of it, what do I know? Well, our vertex is when x is 3, or p is 3, and q is 588. There's our vertex. What does that tell us? Well, x is the number of increases. So after 3 increases, because that's what our x tells us, how many increases there have been, we now have our income. 3 increases gives $588 maximum income. And there's how the quad function can help us to come up with the solution. But you have to be careful. Find the price and number of book sales. That's where we look. Well, what's the price? Well, the final price is going to be 8 plus 2 times. We know there's been 3 increases. So 8 plus 6, the price will be $14. And the number of sales? Well, we know the number of sales is 60 sales. Subtract 6 times the number of increases. Well, there was 3 increases. 60 minus 18 takes us down to 48 sales. So the way for this particular company with these books, they need to charge $14 to get the best combination of sales. $14, 48 sales will yield the best income of $588. There's where you're looking at. Page 18, example at the top, talks about buying 400 articles, whatever they are. Same kind of question. Pause the video, give it a try, and we'll do it together. All right, first thing is we need an expression for the price and the sales. Well, what do we know about the price? We know initially the price was $5, but in this case, we're going to add 50 cents. We're not sure how many times, an X number of times. From there, what's the number of sales? We know the number of sales is 400, but we are going to have 2 fewer sales every time they increase the price, which we don't know exactly how many it is. There's our equation for sales. Let's substitute that. The income will equal 5 plus 50 cents, not 5 cents. 50 cents X times the number of sales, 400 minus 2X. And now we FOIL that to end up with a essentially general form equation. In this case, it works out to be negative 0.1x squared plus 10x plus 2,000. There's our general form after we FOIL. Here we go. Bracket our x's. Factor out a decimal 1, x squared minus, because we're dividing by a negative decimal 1, which gives us subtract 100x. We're going to have to add something in there, plus the 2,000 on the end. Magic number, negative 100 divided by 2 is 50. 50 squared. So it's negative 50. Negative 50 squared is plus 2,500. But we didn't add just the 2,500 because it's in brackets. We actually added a value of negative 250. So let's add the 250 to balance it out. Our final vertex form, negative 0.1 x minus 50 squared plus 2,250. What is this telling us? Well, our p-value is the number of increases. Number of increases in this case was 50. They realized they needed to bump the price by 50 cents 50 times to get a maximum income of $2,250. So they had to figure out over time, okay, do 50 cents more, 50 cents more. They did it a whole bunch of times, 50 times, to realize what they want for a maximum price, or the best price sale combination. So what in the end? Again, the best price is going to be $5 plus 50 cents 50 times they did the increase to realize that. And it worked out to be $7.50 was the best price, because that paired up with the best number of sales, which was 400, subtract 2, 50 times, which yielded 300 sales. So $7.50 per item, 300 sales gives the maximum income in this situation. So there's what you're looking at with word problems. Some are straightforward. Here's a parabola quad function that gets created because of the path of something, and then area and income problems. So textbook, 2 pages. try to do as many algebraically, please, without the calculator. If the numbers are ugly, yes, calculator is fine to practice that. But if you get whole numbers, if you get fractions that should be easy to work with, algebraically practice it. So these deal with the examples we did in the video. Also, the booklet, you can complete the examples and then check the answer key, which is on Brightspace as well. Ladies and gentlemen, word problems, different, just like always. Practice, practice, practice. It'll make life so much easier. Have fun.